Well, in a moment. I'm not sensing the display now. And this is just. Let's see. Oh, that may have been it. Let's see. Yep, there it is. Excellent. Let's see. Let's move out of this.
Oh, shoot. What did she do? No, what the heck? No one plays with it. There we go.
Okay, well, welcome everybody. Next week we'll hear from Mike Duffy on the task and how predicting is really very difficult, especially in the future. This week we have the privilege to have CSI in its full course here.
Not the one from TV.
No, even better than the one on TV. I think the lesson to learn, if you learn anything from today's presentation, is that if you have something that shouldn't be on your hard drive, beware. Anyway, let's welcome him.
Well, thank you very much, Dr. Leedon, and to everyone here in attendance. I appreciate the opportunity to be here and speak to you today. My name is Chris Bross from DriveSavers Data Recovery. I'm one of the engineering team leads there running research and development on emerging technologies in the storage world. And today we're going to talk about something which I think is quite relevant not only to the global population but especially in the education space, because many of you will determine how storage functions in the future. And we'll kind of talk about the status quo of today, where we're going as far as storage technology, some of the challenges that are very tangible probably to everybody in this room today, and what we do about it in the realm of data recovery. As Dr. Leedon said, CSI, the TV show, is of course the dramatic and glamorous end of what we do in the laboratory. I'll try and enlighten you a little bit about that, but as this is more for academia, this isn't really supposed to be a marketing pitch for what we do, but really a technical discussion, so that's what I'll try and focus on. I'm going to pass around a couple of things as well to help initiate some of the conversation. I'll start with the only promotional item which I will do here today, but this is something that for your smartphone or for your glasses, and this is a little microfiber wipe that you can use to clean those items, just pass those on around. And as a reminder to you, why you want to back up your data. Because when I'm done speaking today, you'll probably all be a little bit more paranoid than you were when you walked into the room. That's part of our job, is to help educate people about this stuff. So SSD and NAND Flash devices, secure, fast, reliable, are they recoverable? Well, I'm not sure what you think about those questions right now, but I hope I can provide some answers to you. And we'll provide some definitions as well. Although I assume most of you are familiar with some of this technology, we'll make sure that everybody understands exactly what we're speaking about, so we're all on the same page. Solid state what? SSD, what does that mean? What is a solid state drive? What is NAND Flash? For those of you who aren't familiar with this technology, a solid state drive, is defined as a storage device using non-volatile memory. That, in contrast to a hard disk, which is a magnetic storage device, solid state storage devices are chip-based and typically NAND Flash-based data storage devices. NAND, by definition, is not and, contrary to not or memory. NAND memory is a commodity item now that is the primary type of data storage technology used in solid-state drives. But we'll also talk about why it probably won't be the technology 5-10 years from now. Non-volatile memory, of course, NVM, is memory that is persistent. It stores data. It does not lose data when power goes out. And the concept, of course, is that it retains that data ideally for a long time. But there are some challenges in that as well. So in case you didn't know, an SSD is a solid-state drive or solid-state disk, depending where in the technological world you get your definition. Just for quick reference in the market space, I'm sure everyone in the room has at least one hard drive. The market built about 650 million hard drives last year. A big company like Hewlett-Packard sells about 180,000 hard drives a day into the global space. There were maybe 11 million SSDs built last year. Very small portion, maybe 2-3% of that big number. But look at Apple with all of the iOS devices, who's now shipped 230 million NAND Flash devices. And I'm guessing that a lot of people here have one of these types of devices in their pocket today, whether it be a USB key or a phone or any of those types of technologies. So just for reference, SSDs aren't replacing hard drives yet. They're just eating a small piece of the storage pie. So if we want to look at what an SSD looks like, well, there are many vendors. There are over 200 companies currently selling SSDs. There are now 3 hard drive manufacturers left with the consolidation of the industry. So we can see how the field is changing. Hard drives have been around 55 years, solid-state drives less than 5. They're made up of NAND Flash, as we talked about. This is some BGA mount NAND Flash from Samsung, and we'll talk more about exactly what that looks like as we move forward here. So I'd like to take an informal survey in the room. I do this every time I speak, and I'll ask for an honest raise of your hands here. Who in this room has lost data that was not backed up? Pretty good, pretty good. That's fair. I'm guessing that's about 75% of the people in the room. Okay. Now, aren't we all supposed to know better, especially in the computer science realm? You saw my hand was up too, right? Well, I have a lot of storage devices, and for those of you who have already experienced failure, you understand that. For those of you who have not, you will. Electromechanical failure is really the primary reason we do data recovery, and I want to pass around some devices so you can get a kind of a tangible feel for what these things are. So as we're talking about them, this old-fashioned thing is a hard disk. They're still producing them today. The 4 terabyte single hard disk was announced yesterday by Seagate at $250. Okay? That's the new 4 terabyte coming out. I'll pass these around the room. I also have some SSDs, which is what we really want to look at today. And feel free to play with these. This is not what your storage is supposed to sound like. But these are demonstration units for you to be able to look at what these, what they're basically built of, and pass them around. There's a bunch of NAND Flash inside of this one, and a couple other devices that you can see, whether they be USB-based keys. You can take it out of the bag and just pass it on around. Or camera, flash, memory cards, all of which are these NAND Flash-based devices. And just pass them around the room. They're already damaged and destroyed. Don't worry about getting your fingerprints on them, including on the platter of the hard disk. That's okay at this point. So there's a hard disk. Many of you who lost data probably lost it from a hard disk because it mechanically failed, or you accidentally deleted something, or the notebook hit the ground, or whatever it was. And that's one with a head crash on it, that big ring you see. That's the failure of that device. Electromechanical device with moving parts that spins 15,000 RPMs, that has a fly height down to 2 nanometers of the heads above the platters. It's amazing that hard drives actually work as well as they do for the cost it is to produce them. But we're moving forward into the solid-state technological world, and let's really talk about that. So for those of you who have lost data out there, the good news is we're supposed to be getting smarter about this, right? For all those of you who raised your hand, I hope your next step is to back up all your critical data so you never lose it again. But I'm guessing you probably didn't do that, right? Well, we've got smartphones now, right? Don't these things take care of themselves? We've got iPads and every other tablet that's trying to make it into the market right now. Digital cameras, well, maybe you don't have this anymore because of your smartphone, right? But the digital camera, we don't even print photos anymore onto paper because we can store hundreds, if not thousands, of images on one of those little chips where we trust all that information to be there, hopefully for a long time. It's all about trust in your storage. Is it just blind trust in your storage? Do you even consider the storage that you have that's holding this important data? It's something that you want to ask yourself, and I'm sure you'll be asking more when we get done with the conversation here. So let's look at this up close. There's your data. Do you see it? That's a NAND flash cell. All your information is right there. This is one of those small chips that you see going around the room, basically cut into its wafer level. And this particular diagram is showing you an MLC NAND flash chip where all of the data is stored at a cellular level. Right? Let's look at it up close. This is probably 200 nanometers, maybe 300 nanometers across. For reference, a human hair is 300 times that wide. Okay? So we're looking at a technology right there where your data is stored. What looks like a dental x-ray, possibly to some, is actually the floating gates in NAND flash technology, where a trickle of current pushes electrons across a floating gate to either save your data or erase it forever. Okay? So do you feel a little bit better about your storage now that you know that it's right there? So tangible, you can almost touch it. Not really. The reality is at this nano level scale, things at this density are getting even more difficult to keep reliable. So what is the reality of reliability? Well, one of the strongest selling points of solid state technology is that it has no moving components. It has no electromechanical failure. It doesn't experience head crash. That doesn't mean there aren't issues with the technology of reliability. But if you read the marketing literature, they'll be sure to tell you that failure rates are almost non-existent to extremely low. Well, that is the marketing literature, of course. Hard drive manufacturers will also tell you that their failure rate is extremely low, but all of you have experienced a failure of some sort. So the reality is that the technical information is quite a bit different than what the marketing departments put out there as far as reliability goes. The reality is that all storage devices fail. We're talking about laws of physics here. Okay? It's not a question of if a device is going to fail. It's simply a question of when the device is going to fail, right? I mean, we can all acknowledge that. We understand the technological world in this space. In a hard drive, that's easier to see. You can imagine what's going to break in a hard drive. While in a NAND flash cell, it takes a little bit more knowledge to understand what fails. And we'll talk about some of that here. Failure can manifest itself in many ways, like your partner or spouse in New York City finding your iPhone and not liking what they found on it and sending it 26 stories to the bottom of the garbage chute. That's data loss. It's quite physical and tangible in that case. Or when man's best friend, your dog, is not Data's best friend, and you have to wrestle your SD card out of his mouth, which happens quite often, and we do a lot of data recovery for those types of cases. Or unfortunately, biohazard, aka toilet phone. I hope none of you have experienced this, but to be very honest with you, we do a lot of data recovery for phones that land in toilets. Okay? Data gets lost in many different ways. This might not be the primary ways you were thinking of when we started the conversation, but we'll talk more about that in a moment. But all of this storage is potentially volatile, whether it be a function of the device itself failing or a function of the environment or a function of the user. Data loss happens. But the reality is that component failure on the device is what we really want to talk about today. That's controlled within the actual circuit board, within the NAND flash, within the controller. So let's look at that for just a second. Here's a PCB, a printed circuit board from an SSD. This happens to be an OCZ device. But when we look at this board, which you can look at that Samsung one going around the room for reference, really it's made up of two main components. The controller, system on a chip right here, and then the NAND flash right there. And there's an array of NAND flash depending on the capacity of the device. And sometimes there's some DRAM on there to accelerate caching. This particular design uses no DRAM. So we don't have a potential head crash. We've got nothing spinning. Aside from the interface and the circuitry, that's it, component-wise. That's all that an SSD is built of. But the controller, in this case Sandforce, one of the up-and-coming controller companies who's making maybe 25 companies are producing SSDs based on their technology. It's the brain of the device. It's all the technology of the device. It's the competitive advantages, the intellectual property that one company has over another, whether it's Marvell or Intel or Micron or IndyLinks or SandForce. They're all fighting in this space of controller to lead these drives, just like a RAID controller is what controls a large array of hard disks. The SoC, or the controller on SSD, controls the entire device. Here is the NAND Flash, the other component that we're talking about. This is actually a chip out of an iPhone, sawed in half and X-rayed, showing you 8 layers of NAND, which were that iridescent photo you saw a moment ago. But look at the circuitry break here. Right? There's a micro lead between those wafers that is bad. There's a failure inside the silicon layer here. And basically, there's a failure of NAND Flash. That's not really easy to diagnose externally, as you might imagine. So failures are quite minuscule, and sometimes they're quite hard to get to. But again, it's all about the controller and how it manages that NAND Flash on a device. But what about the recoverability? That's really what we care about in the data recovery lab. When these things break, can we get the data off of them? And with a hard disk, it's a very mechanical function. It's typically a component that needs to be replaced, possibly firmware reloaded, possibly a circuit board issue that we have to fix. But solid-state devices are not always recoverable. Data recovery is not an insurance policy. It's more like an emergency room. It's the thing you never want to have to use, but unfortunately, occasionally you do. But the problem isn't always resolved. The data is not always recovered. Backup, by the way, is your best preventative medicine, in case that's not already clear. We'll try and reinforce that a little bit here. But this is really where a professional laboratory comes in. When we see a failed device, whether it's a USB key or a phone, we have to address it ideally via the controller interface to try and talk to the device using the logic that's already built in to see where the data is, to see what the problem is, to get it off there. Or if not, we're going to end up basically de-chipping the board, taking all of the NAND flash off of the board in attempts to try and use what's called a flash reader and take each individual chip and feed them into a flash reader and then reverse engineer the right algorithms to figure out how data was distributed across the NAND flash in order to figure out where the data you care about lives in order to recover it if we're able to do so. And so when you're looking at that, you're basically either trying to work with the device physically intact, but if you can't do that, you have to take it down to its chip level. Imagine each chip, 8 layers of NAND flash, possibly 16 or 32 chips on a board. Each of those layers needs to be extracted out and then basically built back together as a stitched algorithm in order to create a volume that has data on it. It's reverse engineering completely.
What does it cost to do that?
Great question. I think we're going to save questions till the end, just for the sake of the speed of the presentation, but I'll answer that for you. Backup is cheaper than data recovery, by the way. But we'll answer those questions because they're very relevant. So even at this level, when we get down here, we might not be able to recover the data. We may not be able to get what we need as an image off of that NAND flash. And unfortunately, in some cases, we just tell a customer, that data's not coming back. So what are some of the challenges that prevent us from recovering data on these devices? Most users think that if it ends up in the laboratory, the probability is extremely high we're going to get the data off of it. And it is high, although it's not perfect. And so we don't want to mislead anyone into saying that whatever failed device you have, we're going to get the data off of it. But the big challenges are, encryption. The industry is going to all self-encrypting controllers. In fact, probably half of the devices on the market right now that are true solid-state drives are already encrypting the data at a physical layer level. The user isn't authenticating that. The user doesn't even realize that it's going on. It's really done for 3 reasons. One is obvious security. We're at 256-bit AES, typically in today's controllers. Samsung, Intel, SandForce, all these guys are doing encryption, especially on their enterprise-level devices. But one of the huge advantages to encryption is actually in NAND flash technology having a very balanced bit load. One of the things about NAND flash is it doesn't like to be heavily weighted one way or another with bits. And so encryption is a great way of generating a random bit stream across the actual cell. So therefore, you get a better balance of data across all of the NAND flash cells when you're putting out encrypted data. It has nothing to do with security in that realm. And the other reason is for competitive advantage and adoption in places like banking or healthcare or anywhere that data always needs to be protected and that can't be compromised even at a physical level. Of course, that creates all kinds of problems in recovery. That controller contains firmware. That firmware is the operating system for the device. That firmware also typically contains the encryption keys. I'm sure many of you have heard of firmware corruption, right? It happens quite often on devices. Why do we have firmware updaters? Why do we reload firmware? What happens when you reload firmware on an encrypting device to the globally unique encryption key? It gets blown out. And the device works perfectly fine with no data on it after you update the firmware on one of these encrypting devices if it's a volatile upgrade. So it creates a serious challenge for us where we may not be able to get to the encryption keys to get to the data. Even if we de-chip the device, tear all those images off, what good is that if it's 256-bit locked? We're not going to brute force engineer that. We're not going to get the data off that. So encryption is a huge issue in data recovery. It's great because it protects your data. It's a huge challenge for us to recover. But of course, the industry is more concerned with selling devices and protecting data, as they should be, than the actual recovery of the devices. But we're trying to influence the industry a little bit, not to create a back door, of course, to these devices. That would invalidate the purpose. But to crack open a little window so we can see inside when we need to in a very secured and protected way so that we can actually get data off of those devices. I mean, I don't know, something as simple as an iPhone today is encrypting your data. You may not realize that. But at the user data partition, it's encrypting. You can't turn that on or off. It's happening at that physical layer. But if we've got to rip a chip out of there and get the data off, it creates a separate problem for us. Trim. Anybody in the room familiar with the concept of trim when we're talking about these devices? Okay. Well, I'll define it for you here. Trim is a function specifically for NAND flash storage devices. NAND, as a technology, requires that a cell be erased before it can be written to. Okay? So if that's true, unlike magnetic storage, you can just write to whatever block you want to, NAND flash needs to first do an operation to erase a block before it can write to it. Well, trim says, if I send a file to the recycle bin or to the trash bin, and then I empty that, we all know that on a hard disk, that file's still there, right? It's not deleted. That file, like you said earlier, will be there persistent forever until it is overwritten. Okay? That's magnetic storage. Well, solid-state storage in its first couple generations was the same way. That data would live there in that cell until it lost its retention. But trim says, you threw it in the trash, you emptied the trash, so I'm going to tell the device you really wanted to get rid of it. I'm going to go trim those blocks, which means I'm going to erase them in the background. So a very tangible difference with a solid-state device over a hard drive is that really about starting now if you're running either Win 7, the current Linux kernel, or Mac OS, once you delete a file and empty it, it is gone. You will not recover it with some piece of undelete software. So for those of you who have done that in the past, download a free utility, undelete the files I trashed, not going to be able to do that anymore. That's what trim is. Trimming blocks in the background, erasing them to prepare them for future writes for speed, basically. Garbage collection. Anybody familiar with garbage collection? It's quite relative to trim, actually, where trim is a very specific command from the files, from the operating system to the file system to the device. Garbage collection is a similar function. Garbage collection is always running in the background as a background process of the actual device, not of the system. And it's cleaning up blocks in the background as well. Organizing pages, picking up data, moving it in the background to create more efficient, available pages and blocks to write to. It's collecting the garbage. It's a background task that, again, is prohibitive in data recovery because we may want the data that was out there before garbage collection picks it up and gets rid of it forever. It's basically the same as trim, except it's an auto-running task versus a file system, command sent down. But the end result is that people who deleted a file can't always get it back, or if you have bad file system corruption on a device, the file system itself may think that that's all free space, and then the drive clears it. And this is quite a bit different than hard drives were, where you had a lot more opportunity to recover data in those corrupted states. Well, looking ahead, what's really coming, down the channel here as far as this type of storage goes, and what do we expect to see in the future as we move forward? Well, NAND Flash as a technology really was, I think, first invented 30 or 40 years ago by, I'm failing the name, Dr. at Toshiba, but I can't recall his name. But the technology's been around for a while, and it was adopted into the consumer space maybe 10, 12 years ago with USB keys and flash memory cards and things like that. But really, again, in SSDs, really the last 3 to 4 years is where it's really been growing. But we can actually already see the end of where NAND Flash is going to be. Where we're seeing the changes right now is in form factor. The one I passed around the room, that Samsung, you notice was a 2.5-inch rectangle, 2.5-inch size platter replacement device. That is, the market wanted to take solid-state drives and place them where hard drives were in notebooks. So they made it a 2.5-inch drive, or a 1.8-inch drive, or a 3.5-inch to replace a desktop unit. But that's really not necessary, right? There's no platter in there. There's no required diameter. It was simply to fit in an existing slot. Apple has helped redefine what a storage slot is recently with the MacBook Airs. It no longer has space for a hard drive in it. Hard drive's not an option. You can't even put one in there. So they came up with this new, basically, gum stick factor, which is called an X-Blade. And it connects right to PCI via mSATA for a more direct connection to the motherboard. Why build a bay for a hard drive if you're never going to put a hard drive in a machine? So we're starting to see new form factors. PCI cards. This is an OCZ Revo, which is a high-performance server solution. This is SSD on PCI, a much faster bus, a much bigger pipe to push data, much closer to the processor, much faster. It's quite expensive as well. You can spend $5,000, $10,000 or more on a PCI-based solution right now for an SSD. But we're starting to see that form factor right on the slot in the motherboard with no attached storage. You can get a storage area network, a full SAN, on a PCI card now. Okay? We imagine large storage arrays of hard disks. Well, that's not always necessary when you can put it all on a card and stick it right in the machine. And RAID. RAID, everyone know what RAID in this room is? RAID is a redundant array of independent drives, or inexpensive drives in hard drive cases. In this case, a RAID array is a redundant array of independent solid-state disks. You can see two different forms in PCI, and then there's one built of a bunch of Intel SSDs right there. Why do we RAID devices together? Well, typically for performance and for redundancy. So RAID works the same way with solid-state devices as it does with hard drives. It provides extra performance. It provides extra redundancy. When one device fails, ideally the entire storage array does not collapse upon itself. So that model is still the same as with hard drives, but they can put the entire RAID on a card rather than putting it into a large cabinet. You can read online a lot of recent surveys. In fact, a great one from Tom's Hardware just a few weeks ago, talking about data centers using SSDs in their large arrays and why they're using them. And it's a great article. If you get a chance, or you can email me as well, I can send you a link on that talks more about where these devices are going into the enterprise space. But what about the challenges in NAND Flash moving forward that I alluded to a moment ago? NAND Flash is really hitting a density level now. We're down into the 15 and 20 nanometer production process, and there are issues with density, big issues with density. As NAND Flash technology has gone from single layer to multi-layer to multi-bit, multi-layer, they're simply trying to jam more information into a smaller space and keep the same reliability. The news is that they don't always like to talk about publicly is that NAND Flash is much less reliable at tighter densities, of course, than it is at lower densities. So they add more error correction and control to make it work. They put a smarter controller in place. They over-provision the NAND Flash because they know they're going to have problems with it, and because it's cheaper to produce like that. So the irony is, on one level, they talk about the ultimate reliability of these devices, but in reality, they're severely challenged with keeping them reliable with each generational change and selling them to the public as the next future storage device. But NAND Flash's limitations will hit an atomic level quite soon, and they're already trying to figure out what's next. So regular two-dimensional NAND Flash, like the images you saw up there earlier, probably won't function in 5 years or 10 years. Toshiba is developing three-dimensional NAND Flash technology right now. MRAM, I don't know if anybody's familiar with MRAM, basically magnetic RAM, which is a non-volatile type of storage which is already in the marketplace that might replace NAND Flash at some point using magnetism to hold data rather than using electrons floating through a gate. So it has much better durability and retention over time. I don't know if it would surprise you to know that NAND Flash's retention, that is how long it will hold data over time, on a brand new device that's been used only one time, it might last 10 years. Okay? Some people might think it lasts a lot longer than that. A hard drive might last 50 to 100 years in retaining its magnetic data. But a NAND Flash device that's been fully saturated, that it's been written to enough times to hit what's called its write ceiling, will lose data in about 3 months' time in its retention span, once it's been used to its full lifespan. So these are not archival devices. You put your phone or a camera card on the shelf in your closet and come back in 10 years and try to read it, you will not. It will not be readable. It will, in fact, bleed its electrons out, and the data will be lost. These are all technological challenges that we have in using NAND Flash as the storage medium in these solid-state drives. So the definition of a solid-state drive may change slightly over time as to what the underlying storage technology is, keeping solid-state as the basis of it. So all of that being said, these devices, although they're quite magical in the way they hold data, work quickly, and ideally hold that important data for you for a long time, in reality are quite challenging from an engineering perspective on making them do so. So in summary, the takeaway from a talk like this is, one, all storage devices will fail. Okay? That's a guarantee. It's not, as we said earlier, it's not a question of if, but a question of when. And are you backed up when it happens? Well, if you are, then it's okay that it failed, right? You can just replace the device. Okay? If not, well, unfortunately, you might need a service like ours, professional data recovery. Number two, back up your data. If you don't all have a current backup right now of all of the information that's important to you, whether it's on your phone, whether it's on your computer, whether it's on the camera that you didn't back up and upload to the computer, I highly suggest tonight that when you go home, because Murphy's Law seems to permeate everywhere, I'd hate to have somebody lose data in the near future after you've just learned about why you need to preserve it. Back up your stuff when you get home. Make a second copy that's really important. Consider a cloud-based service potentially for a third copy using encryption. If it sounds like that might be a little bit overkill, well, if you've been burned and you've lost data before, it's not overkill. It's the only way to really protect your information. And consider multiple tiers of backup in order to best protect all of your stuff. And the last point really is, if a failure does occur on a device, no matter what one of these NAND Flash devices it is, first of all, consider whether or not you have any backup. If you don't, be careful on how you proceed with a failure. It's quite easy to aggravate the failure of a device by, in fact, attempting to recover from it. Running repair utilities is typically not a good idea. That is, file system repair utilities or device check utilities or media check utilities on these devices when they're failing. Do not try to defragment them. They don't act like hard disks when they fail. The failures are quite binary. That is, they're either fully functional or they are bricked and dead. If you happen to have one that's limping along in that middle space before it completely dies, don't keep messing with it. If you need the data off of it, consult with us or other professional on what the next best steps are or best practices are before you really create a worse problem than you had to begin with, if the ultimate goal is the recovery of the data. And with that, I'd like to open it up for question and answer. I think we have about 10 minutes left to do that. Anything is fair game here, and I'm going to actually answer your question first, because you asked that earlier, which was
How much does it cost to take in the lab and reverse engineer to get the data off?
okay, excellent question. So the cost of data recovery, at least from a laboratory like ours, is really based on two metrics: the capacity of the device, and then the service level that someone's requesting. For example, do they need it quickly, within 1 day, within a couple days, or within a week? So it's graduated based on how long you can wait for the data. But the average cost of data recovery on a single SSD is about $2,000 to get the data off the device if we're successful in the recovery of, for example, a 128 gig SSD. If we fail to get the data off, we actually don't charge if we fail to get the data off. But that's to get it back in a week. If you needed it back tomorrow, it could cost you $4,000 or $5,000 to get the data back in a day's time, to have a whole team of engineers working on it. But that changes. SD memory cards cost $400 to $500 to recover. Large RAID arrays. In fact, I know we recovered a large RAID array yesterday based on hard disks. Massive capacity devices can cost $25,000, $50,000 or go on up depending on how much storage is involved. So as I said earlier, backup is cheaper than data recovery. Yes, you're next.
I was going to ask if you had a recommendation for a cloud-based service that you prefer or...
Sure. Great question. Although we don't make recommendations as a rule, either on storage devices or on providers, because I'm sure that whichever provider I tell you will end up in the news tomorrow with either a security breach or a massive failure. I'm serious about that. And so, any of those services, there are many, of course. Amazon offers services, eVault, Carbonite, everybody's got a service out there right now. Look for a service that works best for you. Make sure, of course, that they're encrypting the stream on the way up, encrypting the data at their facility, and encrypting the stream on the way down. Do not rely on a cloud-based provider to always hold your data. One reason, well, they're free for small amounts of storage for a reason. It doesn't come with a service level agreement, if you notice. It's a best effort to keep your data up there. Two, half a dozen of those companies went out of business this year. And when they go out of business, your data can go with them, okay, which is kind of scary. And number three, the cloud lives on hard disks, everybody. Hard disks fail. Data centers have issues. I don't care who it is. They have failures in the data center. And I don't care how robust their backup system is. Again, for cloud-based services, remember, all that stuff lives on magnetic storage out there. I think you were next.
Yeah, just two quick ones. One was just in regard to the RAID array that you're storing. What typically fails? I understand how RAID works.
Sure.
Is it typically like a controller failure or multiple disks that hit kind of simultaneously? Like what's more
Great
common?
question. So in a RAID environment, what's the typical reason a RAID goes down? Like, for example, RAID 5 is the most popular level of RAID we recover. RAID 5, by definition, allows for single device failure in an array, well, depending on how many devices are in it, and the array can live in a degraded state. The primary reason that RAIDs fail is multiple device failure, cascading or sequential failure. So imagine that in a RAID array, whether it's solid state or magnetic, when one device goes down, the array stays up. The users don't even notice it, right? An alarm goes off, you're in a degraded state. What happens during rebuild? Well, a new disk is inserted, and all the other drives that have parity information, a small portion of the data from that missing disk, say, we're all going to write back as fast as we can in unison to that one new disk we just put in. So we really heavily exercise all the other disks in the set during a rebuild. Okay? Statistically, we see failures in lots. So one factory in Malaysia on one day had one component issue, and you happen to have 10 of those drives. So sequential failure, failure during rebuild, or cascading failure, where one drive is going down and another goes down at the same time. That's why RAID arrays fail.
Could you say something about, I know a lot of people use optical discs for backup, CDs, DVDs, writable, and I've heard those aren't very good. Do you guys have experience trying to recover?
We do, and we recover them as well. If you're talking about rewritable optical media like CDs and DVDs, well, I like to say that the reason a blank CD costs 25 cents is that it's worth 25 cents. Seriously. You can expect 3 to 5 years, possibly, depending on your storage environment, for a consumer grade type of optical media. There are some much better optical media, types of media out there, and if anyone's interested, you can send me an email and I'll send you back a link to a few recent surveys looking at media. And if you want to use DVD for the long haul, there are better choices. Again, consider a tiered approach where that is only one of your backups. But yes, CDs and DVDs are typically stored improperly. That's one of the biggest issues. And they just don't last that long. Other questions? Yeah.
So you mentioned PCI to M-SATA, the Apple X-Blade. So is that basically a SATA controller and the memory on a single board that plugs into a PCI bus?
No, the SATA controller is actually on the motherboard in that case, but that particular interface that they came up with was in that small device getting directly to the PCI bus with a commodity interface, which is now MSATA. So you're not getting the full performance of PCI, but you're getting the direct connect to the bus. So in that case, that's really just a whole SSD. That Toshiba and Samsung are making that, and OWC are making a solution for that. But it's just, again, either a SandForce, Toshiba, or Samsung controller and NAND Flash, just in a different form factor.
So effectively, you've got a pipeline to the SATA controller on the motherboard.
That's correct.
Rather than...
Yep. And with the current increase in bus speed on those particular devices, you get a big bang for your buck. I own a last generation MacBook Air, not the new one, and my cold boot time from off until opening a document is 12 seconds. And that's good. And it's faster with the new one. No time to get coffee, no time to go to the bathroom anymore. Get right to work. Any other questions? We got about 2-3 minutes left. Everybody concerned about their backups at home? It's okay to be nervous. You know better now, right? Or maybe you all knew better already. But well, if you have any further questions, I'm always available for follow-up. Our company is open 24 hours a day, 365 days a year, just like the emergency room, because you never know when something's going to happen. You can follow us on Twitter at DriveSavers. Oh, one more question?
I have one more question.
Sure.
When you are hiring, what do you look for?
Excellent. This typically turns into a recruiting call at the end of the presentation. What we're looking for, it depends. If we're looking for someone in the laboratory, we're looking for someone with typically microelectronics experience, a double E if possible, or physical experience in the production of storage, whether it be someone that worked for a drive manufacturer, someone that worked for a remanufacturing facility, anybody that worked in optical electronics, stuff like that is what we're looking for in the laboratory. But we have lots of other positions in the company we look for as well, technical marketing, things like that. So,
what would you look for in a CS major, not an EE?
In a CS major, well, someone who's capable of code, of course. We are constantly writing new code. In fact, I was speaking to Dr. Leeden earlier about a project that we have right now where we're reverse engineering the encryption scheme and write algorithms on a particular new popular SSD, which is some serious heavy lifting in code that we're embarking upon now. So yeah, sharp code writers we can always use.
Well, thank you very much.
Yeah. Thank you all for your time. Well, have a great day and good luck on your future.
Thank you.
Yeah, that was great. What are you up to now?
Oh, okay. I'll keep it. Oh, that's okay. Thanks for bringing the carnage back up. Oh, yeah.
See you in the morning, right?
Chris?
Yes.
Okay.
Kevin.
Right. Good to meet you.
Yeah.
Hey, so you guys are at 400 Belmarin Keys?
Yeah.
Yeah, my wife has a studio at 384 Belmarin Keys, so yeah.
Very close.
I'm down there all the time.
What is
Yeah.
it? Probably going.
So you come down Belmarin Keys, you go to the stop sign. Just past the stop sign, the first driveway.
Yeah, those old Bank of Berlin building.
Is that what that
It was, yeah.
Yeah. So she's in a space there.
We're half a block down the road.
So you're around the corner, or you kind of
You
around
keep
the
going
corner?
around that bend, and we're the very last building before you kind of hit that dead space. Sure, you know. Cool. We do. Cool. If you're ever interested, drop me a line. It's already all scheduled. Yeah, if you're ever interested,
I'd love to. Yeah, we're out in the neighborhood a lot, so
please do.
Yeah.
Love to have you in.
yeah, cool.
Thanks for your questions.
I think one of the big advances they made.
How do you?
We didn't make my wife name.
Kind of thing set
Have me free and
Documenting.
Oh, let's get out of here. I know you have a class coming up in here. Yeah. Here, just jam it all in here.
This was the same stick part yesterday?
No, this was not.
Add one
No,
more.
no, I got it. Although that would have been good. My 3-year-old did this yesterday.
Take one of the programs that further make it slightly more exciting, but
I'm gonna go get something to eat.
okay, I have one here.
Go to 351. I was gonna go over to the commons.
We'll let you, yeah. We're going to go home. I'm still in school, I think. Right?
I've got something, but I can do it.
So what do we need for a strategy?
I actually did it Tuesday, or by Tuesday, but I brought the wrong binder today. So I'm like, crap. And so, like, whatever. Huh? I would, but I live off campus. And she said that one time or never. It's okay, it'll work out. I remember today. Oh, it's stupid though, because like, I don't know, this year, coming to school, I'm like, I'm going to be more organized, get stuff done ahead of time. And I know for a fact, if I did this last minute, I would have done it this morning and had it with me. And that's I don't know, that's stupid though. Like, dang it. I think we're just doing. She did the same thing. She just did it in a different form. So I think she did like B equal. I can't remember. She just changed it around. So it's the same thing, but I think she just changed it wrong. At least that was my interpretation of it. Dang it. Huh? I'm actually a junior. Classes wise, I'm a sophomore now, just because I was gone this whole past year. I was in France, and so I didn't get any classes done, and so that's why I'm kind of still doing GEs and things this year. What about you? Freshman? Okay, that's cool. How do you like it so far? Yeah, it's good. Are you going to be a business major or bio? Okay. Okay, yeah. This is, yeah, I think I'm going to go into a business area, so that's why. I kind of just decided that after I got back, so I'm way behind. I'll be here another 2-3 years.
I'll be here.
No, it's the norm now. Ah, that's so stupid. Did it all come pretty easily to you?
Yeah.
Huh?
I use my notes, but
I haven't read the textbook yet because I didn't get mine until this past weekend, and so I did all that without my textbook. And I'm like, I hope this is right. I think this is.
actually it doesn't help that much.
Yeah.
She pretty much covers everything that's going on.
I think one thing that I got a little confused on was this.
I think that it does because it only does not.
Well, how does it affect the opportunity cost of increasing butter production? I was a little confused at like the wording of that question, and then what the it is tough. And so, how does this change?
Because on this one it said like how like the technology for guns gets better, so like it affects the guns, but it doesn't affect that. That's why.
Mm-hmm. Yeah, no, it could have gone like I think at first I wrote that increase in butter production. Wait, crap, I can't remember. I had said something different, but I don't even know what I ended on. I just kind of jumped around. Because I said one thing, and then I reread the question. I'm like, oh crap, it's not that. And so then I changed it again.
You're pretty cool. She doesn't have a teacher that.
No, I like her a lot. I kind of I like French people a lot now, like after being in France. So like when she first came in, I saw how she was dressed, and then I heard her talking like, I think she's French, and I got the French accent confused with German accent sometimes, but I was like, she's French, you're French. So after that, I got so stoked. I'm like, oh, I love this class. Cursor, that's macro.
It's like it's not as bad as to listen to than like just a white guy talking.
Mm-hmm.
It's like a little accent.
It's more entertaining. Yeah. Huh?
What frat were you in?
I didn't do it.
I thought you said you were in frat philosophy.
No, what did I say? Oh, in France.
Oh,
France, yeah. No, sorry, no, I don't do that. Yeah, no. It was amazing. It's sad to be back. Mm-hmm. Yeah. Mm-hmm. And so, yeah, I just was there learning the language more so than anything else. That's why I didn't get anything done. But because I was a beginner in French when I went there.
That's a good life experience.
Oh, yeah. No, I'm totally okay with it. I would do it again in a second.
You saw the Eiffel Tower, I'm assuming.
What was that?
You saw the Eiffel Tower, I'm assuming.
Oh, yeah. Except for I lived in the south of France, which was way nicer than Paris, I thought. But
continuing our discussion of supply and demand. And I think we probably won't be done today, so we're going to finish that up next week on Tuesday. But we should be able to start the real macro materials on either Tuesday or Thursday. So get started with reading chapter 6, which is just a basic introduction about the macroeconomics. So I'm thinking if, depending on how far we go today, I might make the next assignment due next Thursday. Just want to make sure you get enough practice before your first midterm. Okay? So if I decide to make your next assignment due a week from today, I'll post it basically quickly, and I'll email you, so you know you're going to have to check on Moodle. Yes?
What chapters will the exams?
So the exams will be whatever we have covered until that day. So your exam is on a Thursday. So usually what I do is obviously if Tuesday I'm starting a new chapter, that new chapter won't be on the test. I usually cover the chapter which are finished, unless it's a huge chapter that can be chunked into 2. Usually what I do is there's something that we covered the lecture before won't be on the test, because I want to make sure you digest it and that you have time to come and ask me questions. So usually it's whatever we're going to have covered. So I suspect for this one, which is in 2 weeks, it's going to be probably 1, 2, 3, 4, 5, 6. Which is plenty to keep you busy for 2 hours.